Happy Monday. How's it going, everybody?
Great. Happy Monday.
Hey, Mondays.
Welcome,
That's
Josh.
right.
Thanks for joining us. Yeah.
Glad to be
Yeah.
here.
Everyone have a good weekend.
Um, yeah, mine was relatively social. I had a friend who turned 60, and they had a 2-day birthday.
Ooh.
Ooh,
Oh,
that's the way to
thanks.
do it. If you're
Yeah.
gonna do it, right? 2-day birthday.
Party
My
big.
wife, she likes to do birthday week,
Ooh.
which is the week leading up to it. Which ours are 7 days apart. So after
Oh,
mine's, and she's like, "Yeah, well, that's good." Now
just keep the party going.
apparently, yeah. That's cool. 2-day birthday. Oh, congratulations to your friend. 60's no joke. So that's cool. Matt, what'd you do this weekend?
Let's see. I went climbing and hung out with a bunch of professors, basically. So it was
Well, it sounds like
exciting.
an
And
exciting
did some
bunch.
work, of course. There's always work in there. So
Always work
nice.
to do.
Yeah.
Yeah, that's pretty cool. I got to take a airboat ride on the Great Salt Lake. That was really cool. So by very random chance, got an invite to do that. So if anyone in Utah gets a chance to do that, I would say highly recommend it. It's an awesome thing to see.
What's
Or
what's an
what's
an
that?
airboat?
Oh,
What's an
it's
airboat?
a boat, but the how it's propelled is actually a fan on the back, so a
Oh,
giant
okay.
fan. Yeah, and you want that on something like this Great Salt Lake because it's only about 2 inches deep in most areas, and so
Mm,
obviously a motorboat would automatically get stuck.
yeah.
Like you would go absolutely nowhere. But it's kind of fun because you can push yourself over like sandbars and cattails and stuff too. So anyway, it's pretty interesting, but it's a pretty amazing how much it's shrunk.
Mm.
My guide was telling me he'd been on the Salt Lake for about 50 years, and since he's a kid, just boating it, and said it's a fraction of what it used to be. So
Yeah, that's disturbing.
yeah. So anyway, go
Friends of the
check it
Great
out.
Salt Lake, right?
Yeah, friends of the Great
We
Salt
can
Lake, please
fix
support it.
this. Yeah.
Let's hope so.
They might have to rename it to like the average Salt Lake or the
Mediocre.
mediocre Salt Lake.
The has been, yeah. So,
Yeah.
well, that's awesome. So, Josh, good to have you on the show. I think
Yeah.
we met a couple weeks ago actually at Kenji's creator's house in Salt Lake City, and it was kind of fun actually. I think me and Matt had a really good conversation about how you got into doing what you're doing, and that's something we think the audience would love to talk about too. So, I guess for people who don't know who you are, do you want to give a quick intro?
Yeah, I'm Josh Starmer, and I run I run a YouTube channel called StatQuest with Josh Starmer, and I've also written a book called The StatQuest Illustrated Guide to Machine Learning. Um, and
It's a good book,
there
by
it
the way.
is, my book, hooray! And yeah, I teach data science, machine learning, statistics, and stuff along those lines.
So you come from more of a traditional stats background. That is, you weren't strictly speaking a statistician, but I think your training was in traditional statistics in bioinformatics. From
Yes.
your perspective, what was the transition from like pure stats to machine learning and data science like? Because I get that question a lot, and I'm not sure that I kind of have my opinion, but I'm curious to hear your opinion as well.
Yeah, so it's a little funny. I ended up being a little resistant to machine learning because when you're raised as a statistician, you think of machine learning as like an applied branch of statistics, and I was really what do you call it, attracted to the book. What is it? An Introduction to Statistical Learning in
Oh, that's a
R,
good book.
which is a great book, but I also just love the way they call it statistical learning and not machine learning. I'm like, that's right. Stick it to those machine learning people. So I was like, yeah, that's what it was. So it was a little bit of of trying to understand machine learning strictly from the perspective of a statistician. So I think I spent a lot more time than was necessary thinking about standard errors and sort of measurement error and confidence. Like when we think about using sort of modern machine learning techniques like neural networks, uh, things like confidence and standard error are not terms we typically apply to those. And so I think that I still kind of like have this kind of statistician's approach to trying to understanding these things, and it also uh, is one of the reasons why I'm a huge fan of bootstrapping, because bootstrapping allows us to get sort of like some confidence boundary on pretty much anything. Even a neural network, we can get some sense of what to expect in the long term without just like, you know, if we just, you know, usually when we evaluate a machine learning method, we just have what's called a point estimate. You know, we have a single value for accuracy, but we don't have an upper or lower bound or anything like that. And so I guess I do try to, at least, although I don't always teach it from that perspective, I'm always thinking about it from that perspective of how do we know how much we can trust these models? And a single point estimate tells you one thing, but it doesn't tell you the whole picture.
Yeah, that's interesting, because I think there's a lot to be said for the pragmatic approach in business, where it's like, well, we don't know what the p-value is or whatever, but we'll just kind of adjust slightly what we're doing in response to these models. But on the other hand, there can be a high cost to that, right? And sometimes that's not taken into account. Like the signal here is very, very weak. Maybe we shouldn't be doing this thing we're doing.
Yeah, exactly. You have to think about sort of, the practical aspects of how what the effect size is, and how how much is this very expensive neural network going to change things.
That's interesting. I guess when you're starting out with machine learning, do you take the approach of starting with simple statistical models, or do you dive right into deep learning? What's the Josh Starmer approach to problem solving?
Yeah, well, so in my book, I hit statistics really early in the book, with the basic concepts of sort of trying to drive home what effect size means versus what statistical significance means, because they're very different, but I feel like you need both of them. You can't just have a statistical significance and without knowing what the effect size, because it could be very small, and terms of a practical setting, it might be statistically significant, but it may not be practically significant. And so we need to know the effect size. But if we know the effect size alone, we need to know sort of like, well, is that statistically significant? If it's a big effect size, but maybe that's just a function of like, we've only got 2 measurements. And so, yeah, sure, we're going to fit a line perfectly to those 2 measurements, or we're going to make absolutely perfect predictions. But we need to know, like, yeah, actually any 2 random points are going to give us a line that fits perfectly. And so then that's where the p-value helps out. So I try to drive home this awareness that it's important to know both things before we actually get to the machine learning models. However, I'll admit that once we get to the deep learning stuff, I kind of like stop mentioning the statistics things, because it's not very common in those fields. I feel, and maybe it will become more common. I know there's people working in that area to try to make neural networks a little bit more robust to sort of noise and data, because we know that that's what we have. We've got a lot of very noisy data, but right now we're just like, well, it kind of works, so we're not going to complain. I feel like that's the general attitude we have towards more of the advanced techniques.
Oh, Matt, you look like you want to say something.
Oh, I guess part of what we've done with deep learning and machine learning in general is like adopted a different set of techniques, like holding out a test sample and then training on a different sample. That doesn't always happen. It should. And then just checking, okay, does the model do anything on this test sample or not? But to your point, I mean, even applying more statistical techniques in that context could make a big difference. Another thing I might say in general is that I think there's a big problem with statistical just illiteracy everywhere in the world.
Definitely.
We've seen that during COVID. We've seen it. We've even seen it with, there have been accusations the FDA has mishandled statistics for various drug trials. The NIH has declared, and the state of California have declared various substances to be carcinogenic. When you look at the data, it's like, well, that's not statistically significant.
Well, but statistical significance too, I think, is getting an interesting rap.
Yes.
I mean, p hacking is rampant, and so there's I've seen various calls to change that, but we'll see if that actually happens or not. So.
Yeah, I mean, I actually think a lot. I mean, I've actually got some videos on my YouTube channel about p hacking and sort of what it is and how to avoid it. And a lot of it is at least so not everyone knows, there's 2 big branches in statistics. There's what's called frequentist, which is more traditional. And then there's Bayesian, which is a slightly more modern and in some ways a very academic side of statistics. And the Bayesians are always like, p-values are the worst thing ever, because they can lend themselves to being abused in ways that like it's like you can trick other people into thinking your results are better than they really are. But there are ways to kind of mitigate that, and a lot of that is just understanding sort of how statistics works and what it's based on, and how what the p-value means is like random data could generate the data that you observe. Like a random process could do that. The p-value just says it'll be rare, but if you keep testing it and you keep generating new data sets, um, sooner or later, a random process, the whole idea of the p-value is the random process will give you something that looks cool. And about all the things about mitigating p-hacking are all about trying to avoid those false positives and those times when it's just random um, uh, random noise generating. The good thing is like the mitigation strategies are actually relatively simple. You just have to do what's called a power analysis, and the NIH now, they used to not require these for grant applications, but now they require power analyses for everything, which is good. And that is an effect of sort of the p hacking scandal. There was a couple of big publicized p hacking events, specifically, I believe, in the field of psychology, in the field of psychology. Anyways, there were and I think in diet or nutrition, there were a couple of well publicized problems, and now the NIH now requires power analyses, which just basically means you have to determine what the sample size is before you do the experiment, rather than like collecting some data and then going, well, it's not significant. Can we just add 1 or 2 samples to our existing data and get a better p-value? And you're like, okay, now it worked. So that's a good thing. And the other thing is just to like use methods that are good for mitigating, adjusting p-values once you've done them. It used to be before kind of big data, we would you do like one t-test, or you do like one ANOVA. These are kind of like basic introductory statistical tests that tell you whether or not 2 things are different or 3 things are different from each other. It's like drug A and drug B, or drug A, B, and C. Anyways, so you do those things, and those are real simple tests. But nowadays, with like big data, we could do 1 million t-tests, in 30 seconds. And we might, because we have that much data. And when you do that many tests, it's just like what I was talking about earlier. There's a higher chance that a random process could generate interesting looking data. And so you have to adjust your p-values at that point to sort of reduce the probability that you're going to be tricked by just some random noise and go, hey, this looks fantastic.
I mean, so we teach stats, or wait, more to the point, you teach stats. So what are your thoughts on teaching experiment design? I feel like it's teaching statistical methods is awesome, but it's just one element.
Yeah.
These are tools, but knowing how to set these up in a good experiment is I would like your thoughts on that.
Oh yeah. I mean, it's kind of funny that you ask that, because I actually have some videos about that as well. But nobody ever watches those.
Interesting.
But I just got like someone asked some really good questions, on YouTube. They posted some questions in the comments that were really deep, and I was like, wow, someone actually watched this video. And so it's funny that now you're bringing this up in the same week, because is that unusual? Is that like does that deserve a small p-value in and of itself? But yeah, experimental design is critical, because it's funny because not everybody understands that there are different ways to at least so I used to work in genetics, and I worked in mouse genetics, and there are different ways to do experiments. And one way will tell you a lot about a very specific individual mouse, and the other way will tell you a lot about a whole population of mice. typically when we do experiments, we want to learn about the whole population, because that means if I do the experiment in North Carolina and then you try to repeat the experiment in Utah, you should get similar results. You won't get the exact same results, but you should get stuff that is pretty close. Whereas if I set up the experiment in such a way that I only learn a lot about a single mouse, then there's a good chance that if you do the experiment in Utah, you're going to get completely different results. And you're like, well, why would you ever do the one? Why would they even teach how to do the one where you just learn a lot about the individual mouse? We should always just teach about how to do this. Well, there's different utilities. Sometimes we're interested in learning about the whole population of mice, and sometimes we're actually interested in learning about the method we're using. And when we want to measure how well the method we're using works, it makes sense to study in a single mouse and just repeat the experiment on it and see, because then you're holding that mouse constant. And the only thing it's changing is how you're performing the experiment. And that gives us a sense of how much noise we can get just from the individual doing the experiment. And so that's useful. That's a very useful thing to measure. So it's good to do that, but it's also important to set up the experiment where we have what's called biological replicants, where instead of testing the same mouse, say 50 times, we test 50 different mice. And when we do it that way, we can talk about a population of mice rather than individual ones. And that results in an experiment that you could then replicate in Utah. So yeah, stuff like that, experimental design is crucial, because if you do the wrong experiment, then you can only talk about certain things, or you might not end up talking about what you expected you were going to talk about. You have to change your grant or change your publication. Yeah.
Well, and it sounds like this is actually a big issue in practice from what you were telling us before, that like people do design the incorrect experiments and just don't quite get that statistical difference of population versus individual.
That's exactly right. Yeah. So this kind of goes back to sort of the origin of my channel. And I used to work in this genetic lab, and I worked with genetics researchers, and I also I did some work in the kidney center at the University of North Carolina, and they did a lot of kidney research. And I realized that a lot of the people I worked with could use some statistics lingo, but they didn't always understand what was going on. And so most of my early videos were actually created in response to questions that people had for me, or things that I saw people were doing wrong in the lab or just needed a little help with. And so like my videos on population versus, what is it, technical replicates versus biological replicates, sort of what that means. That was done directly in response to a lab meeting that I had in the kidney center. And it was clear that most of the people at the table didn't know there was a difference. So
that's interesting. Yeah, when you said the word replicant a couple of minutes ago, I was like, oh yeah, that's what spawned your videos. I'm glad we're on this topic.
yeah.
And we'll probably switch gears into kind of content mode in a second. But I mean, walk me through this. So you were making videos, for a handful of people. What happened before that?
Yeah. So so I used to work in a lab, and I love doing statistics. Statistics to me is super fun and exciting, because it's to me, it's one of the few areas of science or mathematics that deals with the fact that everything we experience is different. There's always variety. Every time I wake up, the temperature outside is slightly different. The humidity is slightly different. I look at a tree, it's got so many leaves. I look at another tree, it's got a different number of trees. Statistics is sort of like a way that it's like a mathematical way to appreciate the variety that we have in our life, and quantify it and use it to our advantage, use that variety to our advantage, rather than just sort of being overwhelmed by it. So I've loved statistics, and I think it's crazy cool. But I used to work in a lab with a bunch of people that were bench scientists, and they thought statistics was the scariest thing ever. And it was something that they just had to take as an undergrad for like one semester. And they were like, okay, I'm never doing that again. And so part of it, what I wanted to do was explain to my colleagues that statistics wasn't all that scary, but also I wanted to empower them, take something that used to be scary and turn it into something that's a tool that they can use, and that they can fully understand. And also what's helpful is when you really understand statistics, when you're standing by your poster at some academic conference, and someone comes up and they ask you something about the statistics, you don't sound like an idiot. You actually know what you're talking about. So what I wanted to do is sort of arm them with all the information they needed to be a good scientist without making stupid statistics mistakes. And so I used to do these Friday morning seminars that I called stat chats. And I'd say, okay, we're going to have a stat chat on Friday morning at 9 a.m. And people would come and I'd explain what a t-test was, or I'd explain what R squared is, or what a p-value is. But I was an academic lab. And every 6 months, you have new people coming to the lab and other people leaving the lab. So there's always turnover, new students, new grad students, new postdocs, new technicians. And so I was like, I don't want to have to do this every 6 months. I love these stat chats. They're fun. I'm a little bit of a performer. I like being in front of people, but this is, it's getting boring to kind of repeat myself. And so what I decided to do was, rather than repeat myself every 6 months, is I made these little videos with the idea that in the lab, we had a bookshelf that had all the different laboratory techniques. And the idea behind my videos was that it would be a virtual bookshelf of all the little statistical techniques that you would need to work in the lab. And the thing I liked about it was, rather than me just giving the seminar once a semester, regardless of whether it's timely for the individuals, say like I talk about something called R squared, and some of the people in the room might say, great, I need to know that right now. But the other people in the room are like, I don't need that right now. I haven't seen R squared. And it might not be for another 4 or 5 months where they're reading some manuscript and they go, and the R squared was 0.01, and they're like, well, what does that mean? And they probably would have forgotten if I talked about it 4 months earlier, they might've forgotten. So what I like the idea about the videos is, not only was it there for new people whenever, but it was also there for people when they needed the information most. Like at the moment, they could just go, I need to learn about R squared right now. Bam, I'm going to do it. I don't have to wait until the next seminar 4 months from now. And so I have made these videos, and in my first year, I got 9 subscribers and 47 views, which I thought was awesome, right? Because I was only working with 10 other people. So that meant like some of the people had watched the videos, and maybe some of them watched more than one, or maybe watched a couple times. And some of the people from my lab had subscribed to my channel. So it was a huge success for me. Even though by today's standards, that might not seem like very many views. I was really just using YouTube as a tool to solve a very specific problem. And I was making these videos to answer very specific questions that were happening in the laboratory, or, coming up in the laboratory.
Yeah, there's a lot of legitimate skepticism about social media and YouTube and these other channels. It's true, right? It can be a huge distraction to people. At the same time, I feel like we're just scratching the surface of the potential for education. Like when you actually use these tools to teach people things, the impact can just be massive for exactly the reason you're giving, right? Someone doesn't have to be in front of you in the classroom. You can listen to it on your own time. You can listen to it repeatedly. You can go to specific sections. Like there's a lot that can be done here, and I think we're just getting warmed up.
Well, and the cool thing is you already accomplished your original mission.
Yes,
that's right. It was a huge success. And so so often people, they ask me, I get asked all the time, like, how do you make a successful YouTube channel? And I say, make sure your goal for success is reasonable. My goal was to get 10 people to watch my videos, and I've succeeded. And so I was a huge success in my first year. It was, so it's just sort of a way of sort of understanding sort of who you want to talk to and whether or not you're reaching those people. It may be, some people may not be satisfied unless they're reaching millions of people. But for me, my goal was to contact very specific people, and I succeeded in that.
That's very cool. It's interesting. Oh, sorry, Matt, you're going to say something?
No, go ahead.
No, go on.
Okay.
The dog that's about to come say hi. So.
Oh, I see. Okay.
That's great.
What was that transition like for you from just you're teaching, you're using YouTube for that, and then suddenly you become kind of this like YouTube star of statistics. And you told us a bit about like you had to kind of reformat the material. Maybe you could tell us more.
Yeah, something about mice, and people
Something
don't
about
really
mice.
didn't
Yeah.
really
Oh, that's
catch on as
hilarious.
much.
Yeah, that's
So-
right. Yeah. So if you watch my early videos, they're all about mice, and they're all specific, specific to my 10 coworkers, and to the point where like if the data is presented in a specific way to genetics people, that's the way the data is presented to my in my videos. And I didn't realize that like outside of genetics, people look at the data differently, or they'll present it differently, or they're not always thinking about how much mice weigh, and so that was a big learning curve for me. Is I wasn't although I was really excited that that the people I was working with were watching my videos. Sooner or later, other people started watching my videos outside of my small little circle, and yeah, that introduced a few problems in that. And now I had to realize how to communicate in a more general sense to a broader community, and one of the and that was kind of tricky, because one of my original goals of my videos was to translate the language of statistics, which tends to be very abstract, into a language that my genetics coworkers could understand. So instead, typically in statistics class, you'll go there and um, they'll say, imagine you have an urn. And so you imagine there's an urn, and if you don't know what an urn is, it's like a bucket, right? And then you're like, and imagine you've got two colors of marbles in there, black and white, and so they've got this very abstract thing that has absolutely nothing to do with what a genetics researcher has on the table in front of them. So it's something they have to entirely imagine, and imagining things is fine, but it's kind of exhausting. It takes energy, and even if you can imagine an urn full of marbles and of different colors, you then have to imagine how that actually applies to your work, which is mice that have different genes, and or different alleles for the same gene, and you're like, how does this apply? How do I make this abstract thing more concrete so that I could work with it in genetics? And so all of my examples are in the language of genetics, and I don't ever use the urn model, the standard urn model. And I realized that that basically every specialty, like people in finance, people in business, people in healthcare, people in the food industry, they all have their own kind of language with their own lingo and terminology. And they also have their own sort of like ideal examples of like, in mouse genetics, we work with mice. So it's easy to talk about mice and their genetics. But in finance, you might want to talk about corporations and their sort of valuation and their stock prices. You might want to talk about apples and different types of produce if you're talking to people in the grocery store, business, or medical people or radiologists might be interested in X-rays of like, here's an X-ray of like a healed bone, and here's an X-ray of a broken bone. So everybody has sort of things that are familiar to them. And my goal was like originally was like, oh, it'd be great if I could do a video in each sort of idiom, each specialty's idiom, so that people wouldn't have to imagine an urn with marbles and then have to imagine what that urn represents in their specific field. You could just tell them directly, and I think it would be easier to understand. And so, yeah, so my videos have migrated away from all about my mouse genetics all the time, although I still kind of like throw in the mouse reference from time to time just for old time's sake. And they tend to be a little bit more general, but I still always insist on using a specific example for what I'm trying to explain. So instead of it being mouse genetics, I might talk about apples that, different types of apples you see in the grocery store, or you might look at different colors M&Ms in a bag. Most people have had experience opening up a bag of M&Ms, and imagine if you poured those M&Ms into your hand and they were all, yellow. Every single one of them was yellow. everyone can kind of imagine that experience, because usually we see a whole variety of colors. And so once you start talking about it like that, it becomes understandable from a larger variety of people and a larger population and a larger audience. So I've been trying to move that way, but it's been hard for me. And I gotta say, my roots are still in genetics. So that's usually the first thing that comes to mind when I think about trying to explain this stuff. And then I have to go, no. I can mention that. I can say, if you're a mouse genetics person, you might think of this, but for the rest of us, let's think about M&Ms and the different colors we have there.
What I find really interesting is we have basically, 3 teachers on a podcast, which is really rare, actually.
That's
so
true.
yeah,
it's interesting.
yeah, it's kind of funny. And actually, Rosanna, she says, she had another note on abstraction when we're going to get around to it. I guess we just did. But definitely you need to speak other people's languages. You, as a stats math person, become the abstraction machine, and it's your job to see that these are all the same, and then translate between languages. I think it's absolutely true. I mean, Matt used to be a math professor.
Well, and it's funny. This is kind of embarrassing to admit, I've never actually taken a stats class, but where I got my stats was from as an undergrad. So I was a physics major, and then I got a master's in physics. And so you take quantum mechanics. Well, quantum mechanics is all like statistics, basically. And then you take thermodynamics, again, all statistics, except that it's like this very concretized version of the field that then you can generalize more later and say, okay, it's kind of similar to this. When we talk about the expectation value of a particle, we're talking about, it's maybe its average position if you measure it, but it could be just mice, expectation value of mice weights, for example, over population.
Yeah. Yeah, it's cool. Statistics classes. I took some, and they were like the worst things ever.
I hated them too.
Just like the the geneticists I was working with, they were like, I hated my stats class. I was like, actually, we have that in common. I can relate. And part of my problem is I'm a very visual learner. I'm not very good with just raw equations. If you just put a bunch of math on a blackboard or a whiteboard or any kind of board, I'm going to look at that math and go, ugh, and I can figure it out. It's just going to take me a long time. And I got to work. What I have to do is I got to plug in like real numbers like 5 and 3 and just run them through the equation and see what happens to them and see how they get transformed and do it step by step. And it's very tedious for me. And I'm just if I can see it in pictures and I can see it visually, then it's a lot better for me. And so that's what I try to do with my videos, is I try to present everything as a visual element. Instead of describing a residual as the observed minus the expected, I actually show the difference on a graph of like, here's the observed value, the observed weight of the mouse, and here's the value we predicted for that mouse. And we can draw a line between those two values, and that is our residual. And so I tend to be very visual, and that's one thing I really like about exactly. There's my
I mean, I've been looking through your book a lot, and it's cool. I showed it to my kids actually, who are 9 and almost 12, but I mean, the cool thing is you could show them some of the early stuff, especially, and they're kind of like, okay, I get this, like even just visually, right? Contrast that with, I think, how all of us were taught math, especially in university and in graduate level and stuff, and it's super opaque. I took countless stats classes, and several graduate level stats classes, and I got to say, like, I thought they were pretty lame, actually. The way they were taught was, okay, so let's prove all these theorems, but never talking about, okay, so like, how is this actually used, right? And so it was exactly backwards. Whereas your book, I felt like that, somebody might take, especially a math person, because you're supposed to be mathy, but I think something like this would actually be super helpful, I would say, for a lot of students, and especially students that aren't math majors. I mean, the way stats and math, and I think, is taught in general is pretty. We could do a better job. I'll leave it at that. So.
A lot of them, what they'll do is they'll start with definitions, a definition of a term. They'll say, we're going to define the chain rule, for example, and they'll give you a mathematical definition of what it is. And then after they've defined it, then they'll give you examples of how it works. And for me, that's backwards. What I like to do is start with a problem that we can't normally solve without the chain rule and say, hey, we got a problem. What are we going to do? We can't, we just get into a tangle of math. And then what I do is I start showing sort of like what that looks like visually. And then we get this sense of like, so we're working through an example. And in the process of working through the example and seeing how like as one thing changes, another thing changes, and how those changes are linked to each other. And then ultimately we can then define the chain rule once we've kind of worked through some examples first. So that's the way I like to teach, is sort of almost like a dramatic arc of, it's like a romantic comedy where the two people start off like, hey, we met each other, but then something goes wrong, and they have to go off on their own, and they have to grow and learn a little bit about themselves and learn about the people around them. And then they come back and, it's happily ever after. And I feel like that's the way to teach stats, is you introduce this problem, and you're like, well, how are we going to solve this problem? And you end up on this quest or this journey of like self-exploration and statistical exploration. And in the end, you finally solve it. And you're like, holy smokes, we have the chain rule. Not only do I know what it's for, I know how to derive it from scratch, and I feel like that just makes it so much more memorable and easier to sort of know what it is and how it works and all those things.
What about this broader question? Like, I love what you're doing with the channel. My suspicion is that mostly people come to your channel when they're trying to understand machine learning, or they are in a stats class and they need to pass an exam or do a homework assignment. How do we create a more stats literate society? Like, that's a really big, really hard, really important question, but I have no idea.
Yeah. Well, a lot of people have told me that I should write a children's book. And it's possible that I could do that. I've got my little characters in my book. I've got this monster called StatsQuest, and I've got a dinosaur called Normalsaurus, and maybe they could make it easier to learn
So cool.
the basics. But it's a good, it's a big question, and I don't necessarily know the answer to it. However, all I'm trying to do is make it as unscary as possible. I know a lot of people have had these horrible college or graduate school experiences, and they're afraid of it, and they're just like, it's complicated, it has integrals, it has summations, it's got a lot of variable names, it's got a lot of Greek, and there's nothing wrong with the Greek language, but when an equation has too many Greek characters, I start having a heart attack. And it doesn't have to be that way. We can now we don't have to like when we write equations, I think it used to be like that, like you had paper limitations, and you had, paper was rare and expensive, and so it paid off to make things as terse as possible, and to like, we're going to let this Greek symbol represent this massive complicated thing, and we're just going to refer to that Greek symbol from now on. And my problem with that is like, I'll get halfway through the derivation or whatever, I'm like, what does that thing mean again? I can't remember. But there used to be like a financial advantage because paper was expensive, ink was expensive, quills were expensive, to keeping things very concise. But now it's like, it's just a computer screen, and we don't have to be so terse. We don't have to be so concise. Instead of using cryptic variable names, we can actually spell it out. We could say, and actually have a word there that represents what we're talking about, or even a couple of words. And use words in the equations to make them easier to read and easier to understand. So that's one thing I've been trying to do in my videos, is try to, when I see equations, I'll tend to rewrite them so that they're easier to read, and I'll use, at least for English speakers, this makes it easier, English words as opposed to relatively cryptic symbols that aren't always self-explanatory.
Funny side note: I was looking at properties in Greece last night for funsies and maybe for other reasons, but I had PTSD because I was like, oh my god, there's like, they're all
Greek.
I was like, so I'm gonna take the sum of this. What? No,
that's hilarious. Yeah, I remember the first time I went to Greece, and I just remember, oh my gosh, it's all those symbols. I feel like I was spelling out an equation, and I remember like I spelled out like McDonald's or something like that, and I was like, oh, it's in a McDonald's. It's just a restaurant.
Well, it has the American letter of the M too, so the arch. So that's our contribution to the world is that alphabet there.
Yeah.
That's really interesting. Stats Literate Society, I think that's well, data literacy, I suppose that's maybe a
Yes.
related but separate topic. But this could be a 5-hour podcast on its own about just basically like how do you, especially now when I think people could look at the same time on a clock and disagree on that and the time that the clock says, what is, so yeah, it's interesting.
Well,
Before we started, you guys were talking about PhDs. It was a pretty fascinating conversation.
Yeah. What I was talking about, and I assume this is still true. When I got my PhD in 2011, it was certainly true. You would assume that PhDs have a lot of education, and so they would also have access to the best information on careers. But I've kind of found that the opposite is true. So as an undergrad, I'm around all my undergrad friends, and so I know all kinds of career things that I can do, right? I learned from other people, like here's a bunch, 100 things you can do with a physics major or a bio major or whatever it is. What tends to happen in grad school is that your social circle kind of narrows. So you learn more and more about less and less, as they say. And then you don't have access to as much of that information about what career opportunities are. And so as a math PhD, I was hearing things like, well, you can, go to the NSA or you can teach and maybe you can go work at a company. I don't know. Who knows? But I've heard of some people doing that. And the reality is that with PhD, there are all kinds of career opportunities, but there is this big disconnect that happens. And I think you had a similar experience, Josh, especially you were in bioinformatics, which I assume you were told like, well, if you're in bioinformatics, then just go do bioinformatics. Why would you do anything else?
Yeah, exactly. And it's funny because I just assumed that the only place I could really there were two places people worked. And it's funny that there's always just two places, right? I guess if there's one, then you know there's something wrong. But if there's two, there's enough that you're like, well, I guess that's all there is to it, right? But when I was in grad school, there were two places you worked. You either worked in a research university as a professor, and you were what's called a principal investigator. And that meant you applied for tons of grant money and you had your own lab and you had, graduate students coming through all the time getting their own PhDs. And that was one option. The other option was the pharmaceutical industry. Those were the two options for sort of bioinformatics / biostatistics person. And it turns out that there's like a billion options. I just didn't realize it at the time. I just thought that you either did one or the other thing. And so, like, for example, this was not to make myself seem really old, but this was Google was relatively young at the time.
Mm-hmm.
And they would send representatives to the university to try to recruit people. And I just remember thinking, well, there's no way my skills could be useful there, so I didn't even go because I just assumed that data science or working with large sets of data was not really what I was supposed to be doing. I was supposed to be doing t-tests either as a university professor or in a pharmaceutical company, and those were my only two options. And so it was, I know it was a real eye opener when I discovered that I actually could do YouTube as a profession. That definitely was not what I was expecting when I started grad school. So that's been it's been a fun sort of eye-opening experience. I do YouTube. I now work at a startup company called Lightning. I'm doing things that I would have never even dreamt of. In fact, I never did dream of these things. But there's things that, to be honest, I kind of secretly always wanted to do. I just didn't think they were things I could do. And that was, and part of that was because of the PhD and sort of the limit of what everyone else around you is doing. And you're just like, well, that's what I do.
And one of the huge ironies here is that my understanding with bioinformatics is that it really got defined as a separate field because you weren't just dealing with small data lab problems, you were dealing with big data problems. And in fact, as Joe and I were writing our book, it's always fun to brag about that, I guess. As we were talking about the roots of big data, it's like, well, it wasn't just Google, it was things like particle physics and bioinformatics and these other areas where people are having to do this really, really early, and it was really, really hard. And so it got defined as a separate field, like you need to get be an expert in bioinformatics to handle this data, which
Yeah.
would have flowed naturally right into Google, but they
Yeah,
probably
exactly.
didn't realize it either. Like, oh, go recruit bioinformatics PhDs
Yeah,
to do this
exactly.
job.
Yeah, because exactly. But it's still interesting how much and how little I learned as a grad student. I mean, definitely learned a lot. And that's actually where I learned how to start teaching myself statistics. I think
Yeah.
the classes were so kind of bad, but I will say, even though the classes did not teach me a lot of statistics, that's where I fell in love with statistics. That's where I fell in love with this concept that everything's different all the time. And for me, it was like the difference between like looking at the world in black and white and looking at it in color, because now I realize that everything, like I could hold up my socks and I could measure every one of my socks and they would all be slightly different lengths, that kind of thing. And it just, I was like, whoa, wait a minute, everything's different. And even things that I think are the same, like like you could buy 100 of these microphones, but they're all going to be a little different too, right? So even things that are manufactured to really incredibly good tolerances, there's still wiggle room within those tolerances, and that means there's variation in there. So I just fell in love with statistics taking these classes, but I had to teach myself. I found out I had to teach myself statistics in order to see the big picture, partly because of the way they were teaching statistics was equation for this problem. And if you're given another problem, there's another equation. And if you get another problem, there's another equation. And you memorized a bunch of sort of like, it was like a decision tree of problems.
Yep.
If this problem, then this equation. Otherwise, or do you have a lot of data? Yes, I have a lot of data. So then do this or don't do this, or, and we were learning how to do it that way rather than kind of seeing the big picture. And the big picture is the magic of all of statistics, which is variation. And once you understand variation, pretty much all of statistics kind of like falls into place, and you kind of see how it's all related and how all they're trying to do is quantify variation in different contexts, and that results in slightly different equations because sometimes the variation is continuous, sometimes it's discrete. And so you end up with, slightly different equations based on the context, but it's still all about quantifying the variation. And I had to teach myself that, because that was, the way it was being taught was like, there was no big picture. There was no overarching concept. It was all sort of like individual recipes for individual problems. But that's how I learned how to learn statistics and how to teach myself statistics.
Well, it's a different way of learning to see the world too. Because most math classes that you take up to statistics is very deterministic.
That's right.
Right. Okay. There is an answer, and that's it. There's not
Yeah.
a range of answers.
Yeah.
Or possibilities, and it's weird for people to grapple with, because I think that they're so used to being told, okay, so what's the answer?
Yeah.
Well, but in stats, it's like, well, which answer would you like?
Yeah.
So
it's very true. That was actually a really hard conceptual hurdle for me to grapple with, and that's why I had that big enlightenment. I was all of a sudden like, oh, I see it, because I'd taken so much math, I'd done so much math, and 2 + 2 always equals 4, right? And there's never any change from that. Well, the statistician goes, is it really 2? Are you sure it's not 2.00001 and 2.0000001?
Right.
Like, are you really certain? Like, how can you be so sure you only have 2? How accurate is your measurement? How precise is your measurement? These are things that you never think about in a math class. And all of a sudden, I'm like, well, yeah, well, how do I know it is exactly 2? And actually, it's never exactly 2. And that was like, yeah, so that was a huge conceptual hurdle that I had to come over, because at first I just didn't get it. I was like, what do you mean? Of course we get the same answer every time. You plug in the number, you do the math, bam, 4 every time. So yeah, it's true.
Yeah, I remember the early days of big data too. It was interesting because there were conversations that statistics would die, because we had all the information. So what's the point of having statistics, right?
Yeah.
We'll just calculate the answer and that's it. There's no need to sample anything. Why would you do that?
Yeah.
We have all the data. And so it's interesting that hasn't happened. So,
yeah, we've realized the population is always bigger than we want it to be. But that is actually, that was another thing that, now that you mentioned that, that is something that kind of ran into a couple of times when I was doing bioinformatics, and that early on when I was learning statistics, they were like, you'll never measure everything in a population. The population's too big, and so we have to take samples of the population, and we have to sort of estimate what the population is like based on these small samples. Well, actually, one thing that was funny is occasionally when I was doing bioinformatics, I would run into a couple of situations where I actually had the population. And I had every single measurement there was to make about it. Was it the best measurement? I don't know if it was, but it was actually all of the measurements. And I could actually do like population level statistics. And I could say that is the mean. That's not an estimated mean. That is the mean. So every now and then I would be like, yeah, there's something there. But it's true. There's always more data, and there's always more to the story than we think there is.
Well, and there's so many dependencies too, right? I think
Yeah.
the danger is looking at the world as a sort of an isolation of the sample that you're taking or the data set that you're using, but failing to recognize that data itself represents other feedback loops that cause that data into existence. I always teach this when I teach forecasting.
Mhm.
So sales, for example, that's a consequence of countless variables that have happened: supply chain effects, discounts, marketing, consumer behavior, whether or not they have money right now, inflation,
Mhm.
everything, right? Like sales isn't, you can forecast sales, but you think you need to understand what went into that number as well as best you can. And then obviously try and figure out what factors, drove that number as much as they did. So, because I think blindly what happens when people try and do stuff like forecasting is they just say, oh, I'll just forecast this number and extrapolate it out.
Mhm.
And it's always a recipe for disaster unless you understand what drove that data into existence.
Joe, can I get you to make a StatQuest on forecasting? I get asked about that like probably 5 times a day.
That would be awesome.
Actually, I'll take you up on that. I'll make a note.
Yes.
Yeah, I mean, it's
Do a
like
crossover.
That would be awesome. We could definitely collaborate on this.
I just made a note. I will hit you
Hooray.
up on this. Yeah, thanks.
Right. That would be
That's
awesome.
awesome.
Yeah, people ask me about it all the time, and it's yes. Right now, I mean, I don't know. It's obviously one of the most interesting things we can do with statistics and sort of mathematics is try to predict the future and not just sort of like evaluate things we've already done. So I find it fascinating as well. And one of the reasons why I call my YouTube channel StatQuest is that it's actually a quest for me. A lot of the stuff I'm learning, not as I teach it, but I learned it maybe a week before. And so I'll dive into stuff going, I don't know what this is. It sounds cool though. Like neural networks sounded super cool. And so I was like, well, I got to learn about these things. And so that was part of my quest. And so then I created these videos. And so I would love to learn about forecasting, and maybe you can help me with that.
Yeah, it's something I've done for a long time. So,
Hooray.
yeah, it's an interesting field. By the way, for the audience, forecasting is not machine learning. I'm just going to throw that out there right now. I see too many people trying to apply machine learning, like your test set and your cross validation set, and it's not the same thing. So, stop.
So,
what's up,
Joe? I was just curious. Early on, right before we got on the air, you were talking about how your introduction to machine learning, or at least statistics or big data, data science, was via actuarial stuff. Is that where you got introduced to forecasting, or did it predate actually and it led to your interest in actuarial?
I can't remember because I was doing. So we talked about sort of career paths,
Mhm.
with our various degrees. I don't have a PhD. I don't even have a graduate degree. But what I was doing is saying, okay, so maybe I'll pursue being an actuary. This is back in the early 2000s, and like again, your career paths at the time, I think, were very. It was like, let me see, with math, you could become a professor, wait tables, go work for the NSA, or be an actuary.
Yeah.
And the actuary path, I think it's still it's pretty cool. But when I realized that was like a 10-year path of just exam taking and trying to reach fellowship, I'm like, I think I'll find something else to do. And so I did. I mean, and I can't remember how I came across forecasting, but my very first job out of school was forecasting. Like that's
wow.
literally what I was doing for a very fast growing company at the time. And so yeah, then I studied it very, very deeply. You know, very, very. I have just books upon books upon books about forecasting and time series analysis and whatnot. And it's a cool field. I think what you realize very quickly is, you know, there's no such thing. You're always going to be wrong, right? And we talked about that earlier with uncertainty, but this is one area where I think people expect you to be right, and you just really have to be able to diplomatically communicate that well, that's fantasy land. So but you know, but what it does, you know, you want to talk about I guess something or a practice that has direct impact on a business, and you know your feedback loop is right, and also the incentive to be right is pretty high. Is, you know, try forecasting, you know, things like sales or demand or stuff like that, and because the, you know, the impact, you know, if you're right, it means things work, and if you're wrong, really bad things start happening.
Yeah, exactly. You get fired.
Well, and you've been through this, Joe, right? I mean, you were forecasting at a time when the world changed very, very quickly, and we've been going through similar things over the last like 3 years as well.
Oh yeah, I got hired to set up forecasting at this e-commerce company in August of 2008, and then I'm sure you remember what happened in September of 2008, because the financial crisis kicked off and the entire bottom fell out of the world basically. So. And what you realize there is, like, you know, historical forecasting, it's not going to work in this case, right? So you got to understand the limitations of the tools you have. So at that point, I was looking more at leading indicators, like, okay, so like what is consumer behavior at this point, right? How is that changing? Versus trying to say, okay, so let's extrapolate sales, because, well, your sales just fell off a cliff, so there's nothing to extrapolate anymore. So in COVID, I think, was like the you know, the you know, the grandmother of them all when it came to just you know, point in time shifts in everything. But if you were trying to rely on your forecast data from February and extrapolating that forward, you know, 2020, you would have been absolutely you know, in a really bad spot. So it's interesting, but, you know, again, you know, coupling this with applied you know, other applied things, you know, doing lots of optimizations and you know, experiments and stuff like that. I mean, I think all of us have done experiments, you know, whether it's an e-commerce business, and it's just cool seeing like how stats translates to nearly everything. It's such a cool, you know, powerful tool set. So
yeah, I love it. I totally love it.
Yeah, that's awesome. Well, cool. I know we're coming up on time. I know we didn't get to everyone's questions. Actually, Fred has one question for you. What's up, Fred? Yes. Do you offer your message to the universities? Do universities reach out to you about real work and real things that math majors can do? It would help market math departments. You know?
I mean, yeah, probably. I mean, it's funny, you know, I went to a seminar back when I was still working at the university. I went to a seminar held in the auditorium in the building that housed the philosophy department. And the very first thing you see when you go into that into the foyer of that building is a bulletin board with all these little pieces of paper that someone thumbtacked to it. But what it had was like careers for philosophers, and it had all these different things like, you can be an astronaut, you can be, you know, a geophysicist, you know, it's like all these like random things you'd never think a philosopher could do. But that's, I mean, the philosophers, I mean, mathematicians, I guess, have it a little easier in that you're like, oh, there actually are jobs at the NSA. Whereas like a philosopher is like, I don't even know what I'm supposed to do with that. And so they had to like come out guns blazing in terms of like what you can do with a degree in philosophy. And maybe the math departments need to learn, you know, take a lesson from the philosophy department and go, yeah, maybe it's not entirely obvious all of the things. And so, you know, do a census of like 20 years later, what is everyone at the, you know, who graduated from this major, what did they do? And, you know, just make one of those like word bubbles or whatever, you know what I'm talking about, and just put that in the lobby. So when the math major comes in, they go, oh yeah, I could have I could have a YouTube channel, or I could have a podcast, or I could be doing all kinds of things. So I think it's a great idea.
Matt, you look like you're going to say something.
No, I agree. That is a fantastic idea. And I would like us, and I think we're probably all of the same opinion too. On the one hand, I would like more information to get communicated to undergraduates and grad students about career opportunities. And on the other hand, I would like to see more of a focus on career development as opposed to gatekeeping. I mean, I think we've made progress in this regard, but there's still a lot of gatekeeping. And that's the problem with the way stats is taught now. It's taught as a gatekeeping class. Like, you have to get through this class to get your major. and otherwise you can't graduate. Instead of saying, this is really useful information that you're going to use throughout your life, even if it's just being skeptical about things you read in the newspaper or on Facebook.
Yeah.
Well, it's interesting. I'm reading this book called Educated Sheep. It's by the I think former president of Yale. But what's interesting is he's calling out basically this trend where students are going to school basically for the sake of achievement stacking. And at the expense of, I would say, kind of how we all probably approach things. We have natural curiosity. We just want to learn stuff because we're nerds. But most people, I think, are pushed into, their education for the sake of just, achieving more success in life, right? And I think I think all of us have different backgrounds. Like none of us expected to be on a live stream today talking about your YouTube. I don't think you expected to be a YouTube star either, right? But I think it's cool in this field because it's very it's very much a meritocracy where you can come in from whatever direction you're coming in, and there's no one to tell you, no, you can't do this. Did anyone tell you, Josh, that you couldn't do your YouTube channel?
It's funny. I mean, no one I listen to. I mean, a lot. I do. Even today, people are like, "And you can make a living doing that." I got that yesterday at the birthday party I went to. Someone was just like, "What?" And I was like, "Yeah, actually, you can make a living doing it."
That's cool.
And they were like, "No way! I thought you had to be like a video gamer or something like that." And there's that's what they assumed, that everyone on YouTube who made any money, the only way they made it was through entertainment and not through education.
That's awesome. It's definitely inspiring seeing what you've done. I mean, I know Matt and I are just like, it's just cool. I mean, and the cool thing is you already accomplished your mission within the first week of making your channel. So it's kind of like whatever else happens, it's just a big bonus.
Everything else is bonus. Yeah, exactly. It's just a fun, exciting ride.
Cool. Awesome. Well, thanks for being on the show. It's always a pleasure talking to you. Hope we can go hang out again. I think last time we saw each other, we went climbing and then got some hot pot down in Salt Lake. So that was wonderful. Fun. Yeah. And by the way, Josh is a very good cook, by the way. So
yes, that pasta was amazing. So thank you.
That's awesome. Well, cool. What's up?
Well, Joe and Matt, I just wanted to say how great it was to be on your show, and how, I got to be honest, this is one of the better sort of chats I've had online or on a podcast or live stream, because it's stuff I mean, so many things we covered today that I've never talked about outside of this. So this is been very unique for me, and I've really enjoyed it. So thank you very much for this opportunity.
Love to have you back on again. I feel like we can just talk for hours. And so
we got a lot more to talk about.
Certainly do.
Nerds. We're just nerds here. So
exactly. It's fun. I love it. I've got my people.
Well, awesome. For people who want to learn more about you or your fantastic book, how can they do that?
You can just Google StatQuest. Hopefully you'll find my YouTube channel. I've got my own webpage, and the book is available in relatively small markets, North America, on Amazon, but in the next couple of months, it should be available worldwide. I'm actively reformatting it so that it can be printed everywhere. And so look for it soon. If you don't have it now, look for it soon. I'm really excited.
And it's an awesome book. I gotta say, like I've never seen a book with this level of detail that's presented in such an awesome way. So again, congrats on the book. It kills. It's so good. Awesome. So this Friday, we have One Cicada joining us from Data World. We're going to be talking about whatever Juan wants to talk about. He's a smart guy. So next Monday we have Carlene Tarchow from Starburst. Actually, it's going to be talking about some really cool engineering stuff. So that's what I like about the show. You just get a wide variety of people, and the conversations are always, I think, really fascinating. So it's cool. Yeah,
can't wait to hear. I can't wait to find out.
Yeah, awesome. Yeah. Well, thanks for being on. Hope you have a great day, Josh.
You too. Thank you very much.
All right, thanks, and thanks to the audience. Bye.